Welcome to another podcast. This episode, we're going to be taking a look at a technique called the method of characteristic curves. We talked about this a little bit in class already, but essentially what I wanted to go over was sort of the method in general. Describing the method in general requires that we look at something of the form, let's say f of xy, u of x, plus g of xy, u of y. Equals, and I'll just say 0 at this point. And really, the way that I want to go about this is by looking at u of x plus, let's say, p of xy, u of y equal to 0. So here, f and g are the non-constant coefficients. So these are non-constant. They can depend on either of the independent variables x or y. And to simplify this a little bit, I've simply taken and divided through by f, so that p of xy is equal to, in this case, you could say g of xy over f of xy. This assumes, of course, that f of xy is not 0. And in fact, when we looked at this in class, we had f was 1 and g was the constant c. So we were looking at constant examples in class, but I want to explain in maybe a little bit more depth what's actually going on here with the more general case. So as was discussed, the way that I can think of this equation is by appealing to something called the directional derivative. So there's several different notations for this, and so depending on what you used in Cal 3, you may recognize different forms. So let's say that the derivative of u in the direction of the vector 1 p of xy, so obviously that this vector v depends on both x and y, is equal to 0. Another way to write this is the gradient of u dotted with the vector is also 0. Now, knowing properties of dot products, the gradient of u is the vector ux, uy, dotted with this vector, gives u of x plus p of xy, u of y, equal to 0. And so you can see clearly here that these two things match up. That is, this equation here obviously matches this equation here. And so what is going on geometrically here is that when you look at these two statements, both of these are saying that the curve u of xy is constant in the direction of the vector 1p of xy. Now, let's think about the vector 1p of xy. It's the tangent. It's, in fact, if you look at the tangent at the point xy, the vector 1p of xy is the slope of that tangent. And so in particular, p of xy satisfies the ODE dy dx equals p of xy. In other words, this creates a vector field. We know that solutions to differential equations create vector fields, and in fact the vector field that's created here at every single point xy, the function has slope p of xy. And that's exactly what the curve u that we're looking for here has as its property. In fact, if we plot the vectors 1p of xy, we actually create the direction field given by the differential equation. And in fact, u of xy remains constant on this vector field. So the trajectories plotted on the vector field are the exact trajectories along which uxy remains constant. So the basic idea here is, let's suppose that we take dy dx equals p of xy, and we solve that, and the solution here is the function phi of xy equal to c. This is the solution to the ODE. In other words, this is the family of curves in the vector field that satisfy the differential equation. We called those isoclines, if you recall. So the family of curves, the isocline family of curves for the differential equation is this function phi of xy. Then what we know is we can use that to basically say, okay, well, my PDE is constant along those curves. So that means that my solution u of xy is a function, this is not the same f as this over here, is a function of these constant curves. So I think you're going to understand this a little bit better if I do an example with you. In fact, I'm going to do two examples. Let's start off with a really basic example similar to what we would have done in class. If you recall, we looked at the transport equation in class, and the transport equation was u of t plus c u of x equal to 0. And if we apply this method to it, then immediately we say, okay, well, this has to satisfy the differential equation dx dt equals, it would be c over 1. And dx dt equals c has the solution x equals ct. Plus a constant of integration, which I'll call capital C. This suggests then that the curve x minus ct equals a constant. This x minus ct curve is the phi of xt promised by the method I'm looking at up here. So that tells me that my solution u of tx is an arbitrary function of that phi, which means it's an arbitrary function of x minus ct. And if you recall from class, this is indeed the solution to the transport equation or the advection equation. Let's look at a little bit more unfamiliar one with some non-constant coefficients. Let's just replace c with x and see how things change. So let's look at, let's say, u of t plus x. Actually, let me change it up a little bit here. Let's do u of x plus x times u of y, just so I switch around some variables on you. Then the way that this works is dy dx in this case is the ODE that must be equal to x. And if we solve that with respect to x, we actually get, let's see here, that's y equals, the integral of x is x squared over 2 plus an integration constant. So the curve y minus 1/2 x squared is always constant in this case. Those are the characteristics. And so my solution u of xy must be constant along that curve. And so therefore this is my solution. So you can see in both cases it's a pretty easy method. And in fact this is completely analogous to using characteristic coordinates the way we used them in class. In fact, these are what lead to the characteristic coordinates. Here you can see that this x minus ct, we would have called it x minus ct and tau equal to t. These would be the change of variable coordinates that we would need to use in order to make this thing work. The change of variable coordinates down here on the bottom one are a little bit more complicated, but we'll talk about an example similar to that coming up. But this is just the basic method of characteristic curves. It's basically seeing the geometric relationship between the directional derivative and then the solution to an ODE as a vector field, and understanding that the solution to the PDE must remain constant along that vector field. All right, thank you for watching.